Good afternoon, everybody. Welcome to a fun afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. All right, important announcement. This Wednesday, I will be giving test number 1. The way I'll do it is right after our lab on Wednesday, I will send out an email to each of you with the password to open a PDF file that's password protected. You'll download it. It's already available in the assignment area Blackboard. In fact, let me do that now. Blackboard, wrong school, D2L. Sorry about that. And let me just do something that I'll go to student view. All right, everybody see D2L 170 on your screen? Thank you. I'll click on assignments, just like with the lab. Notice I have, this is what you'll see, Chem 170 Test 1. The PDF file is password protected. You can download it now, but you can't start yet because you don't have the password. On Wednesday, right after lab, I'll email it. And because students over the time of the pandemic, when we've been doing things online with Zoom, you'd be amazed all the technical problems that pop up. Maybe you don't, because you might have experienced some. And you'll have until Thursday morning, 10 a.m., take the test, upload your answers to the assignment area of D2L. Now, I put in there the 2CAM scanner and the instructions for taking my test, which is just like the lab, uploaded as a single PDF file. Now, if you don't have a printer, relax. Just write down question number. You don't have to recopy the question and put your answer down. And that you'll scan or take a picture with your smartphone. Anybody have a dumb phone? Actually, cell phone. And then upload it as a single PDF file. The CAM scanner, I want to say scammer, because they do try and scam you to spend money on them. Use the free edition if you don't have a scanner. Also in that files, I have a way of not even using that and making a JPEG files, picture files on your cell phone. And there's a way to convert those into PDF file. That's all in the files you can download. And just shoot your answers up to me and I'll grade it. And one of the things I'll remind you on Wednesday, by Sunday, 1 p.m., if not a lot earlier, I'll grade test number 1. I'll post the scores in D2L. I'll send out an email and post an announcement there. And then by Sunday, 1 p.m., if not earlier, I will send out to each of you an individual email with how many points you receive for each answer on the test, like 1A, B, C, and so on. And then next Monday, a week from today, I will go through the whole test so you can see what you did right or wrong. All right, as I've spoken earlier, test number 1, which is this Wednesday, you'll be able to start taking it, has 3 main areas of questions. One is general knowledge, the other is nomenclature, and the third is reactions. For general knowledge, I don't know, I could ask how many bonds to carbon, hopefully all know 4, and other things like that. For nomenclature, there are 2 main types of questions. One is just like in the problem sets, here's the structure, give the IUPAC, which means the official name of the molecule. And the second type of nomenclature is, here's the name, both common or IUPAC, draw the structures. And finally, reactions will be give the product or products for the following reaction, and there'll be one question, give the starting material, otherwise known as reactants. But if you come from industry, you call them starting materials, and there's only going to be one. And there's 5, yes, 5 bonus points. You pick which 5 you want to be the bonus points. The whole thing just adds up to 105. Any questions about test number 1? By the way, it's in the announcement in the email you got. Test number 1 will cover hydrocarbons, alkanes, cycloalkanes, alkenes, double bonds, alkynes, triple bonds, and aromatic compounds. And with that, what I'm going to do right now is my world famous review for the next test, which is test number 1 in this case. I will have the following caveat, which means, guess what? I don't walk on water unless it's frozen. Even then I stay off it, which means once in a while I'll make a mistake. If I talked about it at least twice in a lecture, it's fair game on test. Once in a rare time, I'll forget to talk about something in a review, but that's rare. But hey, nobody's perfect. At least I haven't met that person. All right, let's get to work. Test number 1 review. Since you all said you could read handwriting, I don't have to go back and reprint this. The following, what you're going to see on the screen, is available in D2L, cleverly hidden in the lecture section with the title Test 1 Review. And let's talk about it. You should know, what are hydrocarbons? Hydrocarbons are molecules with only carbon and hydrogen atoms. There are 2 types of hydrocarbons: saturated hydrocarbons. Again, if it's a hydrocarbon, molecule with only carbon, hydrogen atoms, and only carbon-carbon single bonds. That's a saturated hydrocarbon. You should know unsaturated hydrocarbons, and it starts with UN, unsaturated hydrocarbons. Since it's a hydrocarbon, it will be a molecule or molecules with only carbon, hydrogen atoms. And because it's unsaturated, it will have at least one carbon-carbon double or triple bond. Now, I won't ask you what's an alkane or cycloalkane, but I put it down here anyways. Remember, cycloalkane is acyclic. That means without a ring, saturated hydrocarbon. And cycloalkane, again, I won't ask on a test or the final, but I thought I'd put it down there when I wrote this up a while ago. I think I did ask at that time. I don't anymore. But anyways, cycloalkanes are cyclic saturated hydrocarbons. Next, I taught you how to draw molecules. And remember, important thing I taught you, and this will always be your friend on a test, and that is how many bonds to carbon? 4. How many bonds to carbon? Oops, it's broken again. 4. And I gotta get to fix one of these days. How many bonds? There it works. The carbon, 4. That's always going to be your friend. And that way you can know how many hydrogens. You don't have 4 bonds to carbon, the remainder are hydrogens. And while I'm on screen, time out for a commercial from your host, Dr. White, or a public service announcement. Did any of you happen to think about the fact that when you drove by a gas station, half the weight of gasoline are alkanes? Did anybody happen to cook with natural gas as opposed to electric stove or oven, and think about the natural gas is methane, which is an alkane? Did you happen to maybe light a candle? Think about the candle wax, and half the weight of the candle wax is an alkane. Remember, organic chemistry is all around you. I stole that from SpongeBob. And remember, it won't hurt to think about it outside my class. All right, back to the review. Now, I taught you how to find the longest chain. I think most of you are well skilled in that. And we went through that in chapter alkanes problem set. Now, when we're talking about naming, we talked about the alkane names 1 through 10. 1 carbon alkane is methane, 3 is propane, 10 is decane. And I asked you to learn the chart 1 through 10. It goes higher, but for this class and for most things, 1 through 10 is sufficient. Next, I talked about substituents on a long chain or later on a ring, and we call those alkyl groups. And you should know by now, 1 carbon methyl group, 2 carbons ethyl. When you have 3 carbons, there's 2 possibilities. The end carbon of 3 is called N-propyl. The center carbon of 3 is isopropyl. And when you have 4 carbons, there are actually 3 choices, but the third choice, I think in the last how many decades, I've only seen it used once, which means you're not going to see it. I've only seen it once. But there are 2 per 4 carbons, you see a lot. And 1 is 4 carbons in a straight chain, and the end carbon is attached to a ring or straight chain, that's N-butyl. And my favorite, I love, and I think today we might even find out one of the reasons Dr. White loves T-butyl groups. And that is 4 carbons, 3 CH3s, the center carbon, that center carbon is attached to the chain or a ring. It's called tert-butyl, and I've already started. Organic chemists are lazy. We usually just call it a T-butyl, and I love T-butyl. Isopropyl I like a lot too, and the others too, but there's something special about T-butyl groups. Now you know I'm an organic chemist. All right, real world uses. I misspelled something. Anybody buy any gooseline lately? Should be gasoline. Sorry about that. Did I tell you I was always the first one down in spelling bee? And that proves it. I guess you can blackmail me. Gooseline. No, it's not made from gooses. All right, you should know propane from barbecue is an alkane. Natural gas, Vaseline, baby oil. I didn't put down there, but I mentioned earlier, candles. All right, I only asked you to learn 1 reaction. Here's what I taught you about general reactions. Remember, in this class, we do not balance chemical equations. We're just interested in what the products are. And if you take an alkane or cycloalkane, react with oxygen, this is called combustion. The chemical products are carbon dioxide, CO2, H2O, water. The important thing that's not a chemical, energy, heat, is why we burn things. One of the reasons. All right, next I started talking about alkenes and alkynes. And alkenes is a carbon-carbon double bond. Alkynes is a triple bond. Double bond, 2 lines, triple bond, 3 lines. Now, you should know an alkene, double bond, is made up of 2 bonds, and they're not the same. One's a pi bond, one's a sigma bond. A triple bond has 2 pi bonds and 1 sigma. Now, I don't have down here, but I mentioned it. I should mention it again. Each line or each covalent bond, either pi or sigma, is representing 2 electrons. A covalent bond is sharing pairs. Pairs mean 2 electrons. Now, how do you name alkenes, double bonds? You find the longest chain with both carbons and a double bond in it, and you name that longest chain as an alkane. Now, I have this wrong here. You drop the whole ane ending at the alkane ending, and you replace it with ene. And then for acyclic, you need a number cis for what the lead carbon is closest to the end of the chain. That's for acyclic, plus cis or trans. And thumbs up, people. Everybody see my whiteboard? Thank you. Remember, cis means same side, opposite, trans, opposite side. If we look at the following molecule, after you get outside of not talking about saturated hydrocarbons, when you're talking about things with double bonds, triple bonds, or anything else the rest of the semester, and this will also be your friend on test number 1, 2, 3, 4, and the final. Look at a molecule, look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen, should get your attention like that. And we have a double bond. And how many carbons long is chain? 1, 2, 3, 4, 5, either here 6 or here 6. So that'd be hexane. But it's a double bond. Drop the A and E, put hexene. What's the lead carbon of either of these close to the end of the chain? This is 1, 2. We want the other way, 1, 2, 3, 4. 2 is less than 4 or smaller, and therefore it's 2-hexene. Now, if we have a plane orthogonal, or think about just putting your hand down there or a pen where I have the dotted line, you have two groups, one on each carbon of the double bond. They're opposite sides, like this is the hydrogens is trans, same size, same side, cis. So this is trans. Since this is 2, this will be 3, 4, 5. Oh, look, it's your old friend, the methyl group on carbon 5. So that'd be no, that there shouldn't really be a gap there, but that's fine on a test. Be 5-methyl trans 2-hexene. And remember, cis, same side, trans, opposite. And notice the hydrogens are opposite, which is why I have trans. All right, now, if you have a ring, same thing, name the ring. Don't forget for ring, use the prefix cyclo. Common mistake on test 1. Students forget the cyclo for a ring. And then for a double bond or ring, you name it as the cycloalkane. Drop the A on the ending, replace it with E on E, no number, because one of the carbons of the double bond is always going to be 1. The other has to be 2. When there's one functional group, which is what we're doing this semester in a ring, and then you don't have to worry about cis or trans, because in my career, maybe once decades ago, I might have seen a paper where they had a trans double bond in a ring. You don't see it. And since you don't see it, you don't have to put that down. All right. For a triple bond, you have 2 pi bond, 1 sigma, and you name the longest chain with both carbons of triple bond, drop the whole ANE and replace it YNE. YNE is a triple bond alkyne ending. You need a number. Which carbon is the carbon of the triple bond closest to the end of a chain? Then you do the rest of the substituents. I don't ever remember seeing a triple bond in a ring. In this class, you're not going to. So we're done with nomenclature. Now, reactions, I started showing you how you do reactions. And the first one was hydrogenation. I'll never ask you names of reactions, but I will use them. I just did. And hydrogenation, you have hydrogen gas, H2, plus a catalyst reacting with an alkene, double bond. Catalyst can be nickel, platinum, or palladium. Catalyst just makes the reaction go quicker. It isn't consumed. And you break the pi bond, and each carbon gets a hydrogen. Now, let me remind you about something. And if we look at the following reaction, hopefully you all see it. If not, somebody let me know quick. But anyways, oh, look, double bond. And that's all I see right now, because the rest of it comes along for a ride. And what am I reacting with? Hydrogen. Nickel is a catalyst, which I'll abbreviate CAT. And your catalyst can be, in this case, nickel, platinum, or palladium. And you break the pi bond. Remember, there's one pi bond, one sigma bond, and each carbon gets a hydrogen. Now, here's the second friend on all my tests. And in organic chemistry, do you break carbon-carbon single bonds except for combustion? Rarely. In this case, never except for combustion. Therefore, I start with 4 carbons. I end up with 4 carbons. My 2 carbons is double bond. I broke the pi bond, so there's only 1 bond between them. My general reaction tells me each of those 2 carbons of the double bond now get a hydrogen. And the rest of the carbons come along because you don't break carbon-carbon single bonds. And I know how to put in my hydrogens because I know there are 4 bonds to carbon. Your second friend on all my tests, do you break carbon-carbon single bonds? No. I'll say that again. One of your best friends on all my tests, and the final too, is, do you break carbon-carbon single bonds? No. So don't. Once I started brainwashing is a better word for it, my students' test scores really started zooming up because they were doing some of the weirdest things, which were always wrong. All right, next reaction, double bond, halogen, gas, X2 is halogen is X, and the X can be fluorine, chlorine, bromine, or iodine. You break the pi bond, and each carbon of the double bond gets a halogen. Now, when we add HX, this is now unsymmetrical addition. You break the pi bond, 1 carbon gets H, the other gets X, and that follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the H, the other gets the X. Or as I was taught, the rich get richer and the poor get poorer, which we're talking about hydrogens, not dollars. And just to remind you, I thought I'd give a quick example. And if we look here, what's different? Double bond reacting with HCl, which is HX. Remember, X halogens for this one, chlorine, bromine, or iodine. And you break the pi bond, one carbon gets H, the other gets X. And it follows Markov-Nikod's rule. The carbon with the most hydrogens double bond gets the H, the other gets the halogen. This has 1, this has 2, which is the greater number. Hopefully all pick 2. Do you break carbon-carbon single bonds? No, but the pi bond, I do and I did. And the hydrogen goes to this carbon because the 2 hydrogens are already there. The halogen, in this case, chlorine, goes there. And I know there are 4, yes, 4 bonds to carbon. I can put in the rest of the hydrogens. By the way, the chlorine counts as 1 bond, just like a hydrogen. All right, now along the same lines, excuse me, if you add H plus, and that means acid catalyst, H plus means acid catalyst, and water, think of water as H and OH, hydroxyl group. You break the pi bond, one carbon gets H, the other gets OH, and it follows Markov-Nikod's rule. Now for triple bonds, you have not 1, but 2 pi bonds. And here we have hydrogen, but now bracket X, then S, close bracket. Whenever you see that, that means excess. That means you have all the hydrogen in the world that can react with anything hydrogen can react with. That's the organic chemist's lazy way of not balancing an equation or even have to think about balancing it. And again, you use a catalyst, nickel, platinum, or palladium. Since you have 2 pi bonds, each one, when you break, each carbon of the triple bond gets 2 hydrogens. And the same thing with halogenation. If you have a triple bond, 2 pi bonds, X can be chlorine, fluorine, chlorine, bromine, or iodine. And once again, since we have 2 pi bonds, I don't want to balance this chemical equation anyway. I use the chemist shorthand trick, bracket, letters XS, close bracket, meaning I have all the excess or all the halogen gas that anything halogen gas can react with. And here we have 2 pi bonds, each carbon, because of that, gets 2 halogens. Next, I talked about aromatic compounds. This is benzene. Benzene, I can either draw with the calculus structures, these 2, or this is called the pi cloud circle, or other names too. I like the first 2, I just think it looks cooler. But if you do the second one on a test, that's fine. And this is toluene, a methyl group on a benzene ring. And those are the IUPAC names. Now, since this happened on one test, and the student lost 10, 12 points out of 105, which is not good, if I ask, draw the structure of benzene. You can either do this as a 6-member ring, and here's the other resonance structure, or you could draw it with the pi, delocalized pi cloud. This is correct. Any one of these 3. You do this and forget the stuff inside, the double bonds or the circle, it would be wrong because this is cyclohexane. Be sure to put the stuff inside the ring like you see here, here, or here. And I say that now so you won't make that mistake on Wednesday. Now, when it comes to disubstituted benzene, and this is only for benzene, not cyclohexane, that's a common mistake students have. You have ortho 1,2 disubstituted, meta 1,3, para 1,4. And later today, we'll go through the aromatic problem set. We'll cover this. Now, I talked about new substituents. Cl chloro for chlorine atom on a benzene ring. F is fluoro for fluorine atom. Br is bromo for bromine atom. I is iodo you have for an iodine atom. And O2 is nitro. There was sulfonic acid, but I won't ask you to learn that. Now, when you have a benzene ring, you're not going to break these double bonds. You're not, because then it's not as stable. It's very hard to do that. Can be done, but in this class, let's think of, no, you're not. So we have what's known as electrophilic aromatic substitution reactions. And that's where we replace one of the hydrogens on the benzene ring. Remember, each carbon of benzene ring has a hydrogen. And for halogenation, you need a catalyst for benzene, which you don't for an alkane or alkyne. And here, we usually use chlorine or bromine. I have never seen it with other stuff. And you need a catalyst now. That's ferric trihalide. And you replace one of the hydrogens with a halogen, chlorine or bromine. When you have benzene reacted with nitric acid, HNO3, and sulfuric acid, H2SO4, you put an NO2 group, not NO3. I'll mark it wrong. And if you take sulfur trioxide and sulfuric acid, H2SO4, and react it with a benzene ring, you put on a sulfonic acid. Remember, it's SO3H. Don't forget the H. Now, as I mentioned when we in class, and not this week, but next week we'll do a lab, talk about it. When something is already on the ring, it acts as a director. In this class, for my test and final, I will not be covering directors, but we will cover it in the lab, so you'll not walk away ignorant, hopefully, God forbid, ignorant from my class, not knowing all the good stuff in organic chemistry. So what that means is these three reactions are the only three I can ask on an exam. And now let's look at Friedel-Crafts alkylation. That's when you take a benzene ring, react with alkyl halide, RX, in the presence of a catalyst. And the catalyst you need is aluminum trihalide. For this one, I've only seen it done for bromine or chlorine. And you put an R group on here, something very special, very rare. And the carbon with the halogen is the carbon with the bond to the benzene ring. All right, I'd like to do something right now. Now, the question I'm going to, it says on there, are you done? But I'm going to ask you, did you like the, was the review helpful? Again, the question, yes or no, was the review helpful? All right. I'm glad it was helpful. I already knew the answer, but I still wanted to check with you. What that means is for test 2, 3, 4, and the final, I'm doing a whole week, we'll do reviews and it's help students. Before I move on to the aromatic problem set, are there any questions about the review so far or test number 1? Remember, in my class, there's no such thing as a dumb question ever. All right, let's move on. But before we move on, it's time for a public service announcement from me, Dr. White. Don't forget tonight, I will have from 5 to 6:15 my office hour on Zoom. If you have any questions whatsoever, stop on by. All right, let's look at the aromatic problem set. And the first question is, oh, it's a nomenclature question. Give the IUPAC name for the following. And a methyl group on benzene ring. Do not put down methyl benzene. That's a mistake on test number 1. I see students. That's toluene. Now, if we look at B, oh, we've got a methyl group on the benzene ring and NO2. Now, this is considered disubstituted, even though the word toluene incorporates the CH3 on a benzene ring. So the base name is toluene. NO2 is nitro. Notice it's 1,2 disubstituted, and that's ortho. So that's why it's ortho nitrotoluene. Remember, 1,3 is meta and 1,4 is para. Speaking about, we look at C, we have an ethyl group and a isopropyl group on benzene. So we have benzene as its root name, ethyl isopropyl. Notice it's 1,4 disubstituted, so it'd be para-ethyl isopropyl benzene. Now, since I am not enforcing the alphabet rule, don't tell anybody I'm being nice, remember. But if you had put down para-isopropyl ethyl benzene, I would have marked it correct on test 1. And the final 2. Now, if you have more than one group, as in E, each one has a number. And remember, 2 is di, 3 is tetra. And notice I have not 1, but 2, but 3 bromines. So the base name is benzene, Br is bromo, and there are 3 of them, tribromobenzene. Well, if you see tri, I need 3 numbers. And I call one of them 1, keep on numbering them 3, and the last one is 5. So that'd be 1,3,5 tribromobenzene. Now, the other type of nomenclature question is give the IUPAC name for the following. I asked benzene, how do you do that? Well, you can draw the resonance with the double bonds or the circle. You just put a 6-member ring, nothing inside. That's cyclohexane, and I mark it wrong every day of the week. And weekend too. Well, the weekend is part of the week. All right, now, how do you decode para-ethyl chlorobenzene? You start from the right, move left. Benzene, 6-membered ring. And we have here, and I think I had the wrong alphabetical order, which is why I rewrote it here. We have ethyl and chloro. Cl chloro, ethyl, 2 carbons, and they're para, 1,4. Now you could have put the ethyl group on top and a chlorine underneath, and that would be perfectly correct also. So all you're doing is flipping it. If we look at C, metabromotoluene, well, if you start from the right, toluene, methyl group on a benzene ring. Don't forget the lines inside. And bromo, Br, and that means 1,3. Now, probably none of you wrote it this way. Let me show you how most of you wrote it. You got it right. Forgot what the other substituent was. And this is 1, 2, 3, and there's a bromine. Now I drew it this way, putting a bromine on top and the methyl group here. If you put a circle inside, that'll be all right. All I've done is rotate it like this. My thumb is the methyl group. If I go like this, it's the second structure. And the bromine flips too. Aren't you glad I know this stuff? So whatever way you write it, if it's correct, I'll give you the right points. All right, let's do some reactions. A and B, halogenation, X2, Fe, X3. This is putting a chlorine on the benzene ring. This is putting a bromine on there. That's the only two reactions I can ask you on that reaction. Let me go to the end, I'll come back. If you look at F, we have SO3, H2SO4, and we put on a sulfonic acid group. Don't forget the H, SO3H. Students do, they just put down SO3, and I mark it wrong. Make sure you put the hydrogen there. And nitric HNO3 and sulfuric H2SO4, you replace the hydrogen on the benzene ring with a nitro group. And finally, let's go back to this. If we look at C, I have a benzene ring. I'm reacting with CH3Cl, methyl chloride, AlCl3, aluminum chloride. That's Friedel-Crafts alkylation. And here, benzene ring plus RX with an aluminum trihalide catalyst, and X can be chlorine or bromine. I didn't put it down there, I should have. Bad Dr. White. And the carbon with the halogen will be the carbon bonded to the R group in the benzene ring. And here I only have one carbon, so there it is, toluene. Now, if you notice E, benzene ring, carbon, carbon, oh, alcohol chloride. This is my R group. I have my benzene ring. Then my benzene ring is bonded to this carbon of the cyclopentane ring to make that molecule. Oh, I should warn you. Often on a problem set, I'll put a couple of harder ones, harder than anything I'd put on a test. If you can do those super hard ones, then the ones I put on a test will be no problem for you. And I think we're done with the problem set. Any questions on the problem set, aromatic compounds? Oh, I've been hogging all the fun. I better let you try one. Give the organic product or product for the following reaction. 3 points each. Thank you, Joe. Thank you, Megan. Thank you, Tam. And Calvin, do you need, thank you, Calvin. All right, try and give everybody time to finish. So if we look at this reaction, what's different? Ooh, a benzene ring. That's different. Remember, look for what's not a carbon-carbon single bond or carbon hydrogen atom. Carbon, carbon, carbon. Ooh, carbon with a halogen. That's alkyl halide. Aluminum trihalide. Remember, X can be chlorine or bromine. This is Friedel Crafts alkylation. You put an alkyl group R on a benzene ring. Remember, the carbon with the halogen is the carbon that this bond goes to. Well, it's the N carbon. Do you break carbon-carbon single bonds? Well, my general reaction tells me I have a benzene ring and my R group is this, 4 carbons. Which carbon has the halogen? The end one. So I have 1, 2, 3, 4. I know there are 4 bonds to carbon, so I can put in my hydrogens and I'm done. Now, if you put that benzene ring on another carbon, I will mark it totally wrong because part of this reaction is understanding which carbon that will be bonded to. Now, one of the things, oh, I should mention, I still have the fastest mouse wheel finger this side or the other side of the Mississippi. And if you need to see something moving away from that screen, yell, hey, stop, I want to see it, or anything else to have me not move. All right, let's move on. Now, on test number 1, I'll have one synthesis, which could be any of the general reactions. And why don't you try this? And what would be the starting materials for that reaction? That would be 4 points each on that one. Synthesis are higher points because there's more work. All right, I think everybody's almost done. All right, let's get going because it's right around break time. So what's different here? Ooh, benzene ring. That's different. And it's got carbons on it, which I'll call R. And this is R. And I've got a catalyst, aluminum trichloride. Which I can abbreviate aluminum trihalide, where X can be chlorine, which in our case it is, or bromine. And what are the 2 things you react? One of them is a benzene ring. The other is my RX. In this case, X is chlorine. What's my R group? Isopropyl. Remember, the carbon with the bond to benzene ring is the carbon with the halogen. So here, one question mark would be benzene, and the other 3 carbons would be this, isopropyl or 2-chloropropane. And that's how you do it. And Oh no, I apologize. I went a whole minute into our break. Why don't you let me look at my, why don't you come back at 1:56? It's time for Dr. White to get up and stretch, and you can take a break for 5 minutes too. Be back in 5. Time to get going again. And I hope you're all back. Does anybody have any questions about anything to do with aromatic compounds or any of the other areas for test number 1? Well, I know what I can do. I can ask it as a poll question. Now, instead of "Are you done?" answer the question, is there anything else I should, do you have any questions for anything dealing with test number 1 material? All right, I can move on. And I'm glad I stayed, postponed test number 1 by a week, because I think this will help you do better on test number 1, which makes me happy. It's always good for me to make myself happy, and having students do better on tests makes me happy. All right, let's get back to alcohols. Remember, this will be on test 2, not this Wednesday. So let's get back to where we were. All right, we're talking about reactions of alcohols. And the one I showed you was thionyl chloride, SOCl2, reacting with an alcohol. And you replace the hydroxyl group with a chlorine on the carbon that has that hydroxyl group of the alcohol. And I think I showed you how that in the previous reaction, reacting an alcohol with HX, are one of the 2 ways I'm sure the company Splenda makes their product, the sucralose for their product. Whoops, that's not what I want. That's what I want. And here's one for you to try. Give the organic product or products for following reaction, 3 points each. Remember, this is test number 2 material, not test 1. And when you're done, give me a thumbs up. And if you're done early, please be patient. I try and give everybody time to finish. All right. I think we're done. Now, I'm going to say this a million times, but it's how I look at a molecule. When I look at an organic chemical, I look for what's different, what's not a carbon-carbon single bond, what's not carbon-hydrogen, ooh, oxygen with a hydrogen, carbons, alcohol. And reacting with SOCl2, and you replace the hydroxyl group with a chlorine. What's my R group? This. Do you break carbon-carbon single bonds? No. So I'm going to have my ring. I'm going to have my methyl groups. And which carbon has the hydrox group? That one, which is this one. And that will get a chlorine. And that's how it works. Now, on test 2, unlike test 1, I'll have 3, maybe even 4, but usually 3 synthesis problems. So for this, it can be for any of the reactions I talk about. So let's try one. What molecule do I react with thionyl chloride, SOCl2, to make that molecule? All right. I think everybody's done. So let's go ahead and do this. I'll give you another 8.7 seconds. 8.2, 8.6, 8.65. Time's up. If I look at this product, what's different? What's not a carbon-carbon single bond, carbon or hydrogen? Ooh, a chlorine on a carbon. What's that? Alkyl halide. But in this case, I'm going to even just call it this. Why? Because I'm using thionyl chloride. And what do we have to start with? An alcohol. What's my R group? This whole thing here. Have I added any carbons there? No. So I better start with the same number of carbons, and they're connected the same way. 4 across and 1 methyl. This carbon here has the halogen, which will be the carbon here with the hydroxyl group, this one. And I now know there are 4 bonds to carbon, so I can put it in my hydrogens. And does everybody see that? Okay. All right, let's move on. Now, the next thing I'm going to talk about is the oxidation of alcohols. Now, before I talk about this reaction, there's something I have to teach you. So I will. Now, what I'm about to teach you, click, the switch is off. This won't be on a test, but I will use this terminology in class throughout the rest of the semester. So it's something that will be useful to know. Now, when we talk about alcohols, there are actually 3 different types of alcohols. Remember, R can be anything with carbon and hydrogen. Now, in math, remember you can have X, Y, and Z as variables. Well, by the way, this is called a primary alcohol. I'll never ask that on a test, but I will use that terminology. 1 R group on a carbon with a hydroxyl, OH. Now, what if I have 2 R groups? And notice I made this thing called R prime. And that's like an X and Y, and R prime can be different, which they are, or they could be the same. And we call this a secondary alcohol. Two R groups on the carbon with the hydroxyl group. And you could have three. And to show these R groups could be different, they could all be the same, but they could all be different. I'll use prime and double prime, just like in math, we use X, Y, and Z. And this is called a tertiary alcohol. Again, I'll never ask on test or final, but it's terminology I'll use in the class, and we use in organic chemistry. Now, organic chemists are lazy, so a shorthand for primary is the number 1 degree sign ROH. For secondary, a shorthand is 2 degree symbol ROH for secondary, and the last one, tertiary, 3 ROH, alcohol. So we have one R group on a carbon with the hydroxyl, primary, 1. 2 R groups that can be the same or different, which is why we use R and R prime, that's the secondary alcohol. And finally, on this same carbon with the hydroxyl group, we have not 1, not 2, but 3, and they can be the same or different. That's why you use R prime and R double prime. And that's a tertiary alcohol, which is abbreviated by 303. So primary, secondary, tertiary alcohols. And I'll be using that terminology, but I will not ask it on a test. What's a primary, secondary, tertiary alcohol? So let's look at our first reaction. Now, this is called oxidation of alcohols. And here I have a primary alcohol, which I could have written this way. I'm oxidizing it. Now, in organic chemistry, this means oxidation reagent or chemical. And there are different oxidation reagents. I'll teach you later on, KMNO4. Actually, we use that in the lab on alkenes and alkanes. Don't forget that lab is due on Wednesday. I made a mistake on the date on the first lab, and I think all but one of you have handed it in. I have posted the scores for that lab. I've graded it. It's in D2L. I'll talk more about that on Wednesday. Now, if you take a primary alcohol, that's a primer, and you oxidize it, and instead of forcing you to learn all the different oxidation reagents, such as potassium permanganate, sodium dichromate, potassium dichromate, and others, I'm going to just use the symbol bracket O close bracket. And O stands for oxygen, because oxygen gas can oxidize things too. And what happens is you lose a hydrogen here and a hydrogen there, atom, and you form a carbon oxygen double bond. And this is, we'll learn later on when we get into that chapter, is called an aldehyde. And you'll learn later in the semester, Dr. White and Mother Nature love aldehydes. My first and last patent, or first patent and a couple others, I use my knowledge of aldehydes that nobody else figured out to make new things. So I like aldehydes. And my PhD research, I did this reaction. So let's take a look at it. And the question being, give the organic product or products for the following. We look at this and what's different? Hydroxyl group on a carbon. And notice this is an alcohol, but it's a primary alcohol. And this is my R group. Excuse me. And it's a primary alcohol. And when you oxidize it, that's what the brackets with the O is. You lose a hydrogen here, hydrogen there, and you form a carbon-oxygen double bond. Well, do you break carbon-carbon single bonds in this reaction? No. So I have 3 carbons. I better end up with 3 carbons. The carbon with my hydroxyl group is the carbon double bonded to oxygen. And there's 4 bonds to carbon. I didn't mention it. Notice this counts as 2 bonds. 1 more. So I need 1 hydrogen to get the 4. And the other 2 carbons, I know 4 bonds to carbons. And that's how you do this reaction. And why don't you try that one? What would be the organic product or products for the following reaction? Half the class is done. Let's be patient. Give people a little more time to finish. As you notice, we're getting into more sophisticated and fun reactions. And whoever was dreaming of a rainy day today, thank you, because my lawn needed it. So did my trees and bushes. All right, I think everybody's done. Let's do this. What's different? Ooh, oxygen with a hydrogen on a carbon alcohol, but notice the O in brackets oxidizing. So I have to look, is this a primary alcohol? And the answer is yes. When I oxidize, I lose a hydrogen there and there. My R group is still bonded to that carbon, but that carbon will be double bonded to oxygen, also have a hydrogen. We call that an aldehyde. What's my R group? This. So do I break carbon-carbon single bonds? No. Here's my carbon here, which is this carbon, which will now be this carbon, double bond to oxygen with a hydrogen. And I know there are 4 bonds to carbon. And I'm done. And that's like, oh, let's do another one. And why don't you try this one? And that's the cyclohexane ring. No, I didn't forget the bonds. inside the ring, there are none. All right, I think everybody's done. Let's look at this molecule. What's different? Ooh, carbon with a hydroxyl group. But it's also got carbons on it. And we're using an oxidation reagent, which is what O in brackets is. So this is a primary alcohol. When I oxidize it, that's what this means. I lose a hydrogen there, and I form a carbon-oxygen double bond. So if I lose a hydrogen there and here, here's my R group. Do you break carbon-carbon single bonds? No. And that's the molecule you get. Now on test two, I'm already ahead of myself. There'll be a couple synthesis problems. What would you react with an oxidizing agent, bracket O, close bracket, to make that molecule? In other words, give the starting material for that reaction. And this is the fun part of organic chemistry, what I call synthesis. How do you make something? But then I'm biased, I'm a synthetic organic chemist. All right, anybody need more time? Okay, if I look at this molecule right here, what's different? By the way, I'm oxidizing something. Ooh, oxygen, double bond to carbon, hydrogen, and on that carbon, this one right here, they're carbons. And I'll call this my R group. And what do we oxidize to make a aldehyde? And we'll have a whole chapter on this. We start out with a primary alcohol. And therefore, here I have my carbon with the double bond to oxygen will be the carbon with the hydroxyl group. My R group is 2 carbons. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's how you do it. So when you oxidize a primary alcohol, you get, we'll learn later on, an aldehyde. Now, similar is if you take a secondary alcohol. And secondary alcohol, another way I can draw it, and you oxidize it, that's what the O in the brackets mean. Again, you'll lose this hydrogen, this one, and you'll get this molecule. It's similar to the last one, except instead of a hydrogen here, we have R prime, and this you'll learn in a couple of chapters. It's called a ketone. And Dr. White, Mother Nature, love ketones. I really do. My last patent, US patent, I used ketones in a way nobody else had ever used them to make a product that helps make car engines and other things in a more environmentally friendly way, which is a good thing. Also made the company I had working at a lot of money. So secondary alcohol oxidize, you get a ketone, carbon, double bond to oxygen. But now on the carbon with the hydroxy group, there's not one, but there are two R groups, R and R prime. Now, one of the habits organic chemists like myself do, sometimes we'll write a secondary alcohol like this, or sometimes we'll write it like this. And both of these are the same. And I'll do either on a test. It's just part of organic chemistry. And if I were to take this and oxidize it, what do we have here? We have a secondary alcohol. First, look for what's different, hydroxyl group on a carbon, and then one of these I can call R and the other R prime. Doesn't matter which you call which. But if we look at the second one, it's the same molecule. I call that R, and I'll call that R prime. And in our general reaction, when you oxidize it, you lose this hydrogen, and form a carbon oxygen double bond, a ketone. So if the same thing happens, here I'll lose these two hydrogens, and what's attached to that carbon is the same thing. Now, if I did the second structure, let's call this A and B, and I'll lose hydrogen here, hydrogen there. There are 4 carbons, R prime and R, and I'll form that. And these two are the same molecule. I'm just drawing it slightly differently. And that's how you make ketones by oxidizing a secondary alcohol to a ketone. And a couple of chapters, we'll have a whole fun time with aldehydes and ketones, and Dr. White will be really happy. Now, there's one other thing which I couldn't do in a primary alcohol, but I can do now, and that is the following reaction. And if we look, we've got an alcohol in a ring. Now, I can say this is R, and this is R prime, and they're just connect together. So what I really have above is a secondary alcohol. But in the ring, R and R prime are connect together. If I oxidize it, just like you saw above with a secondary alcohol, I'll lose this hydrogen, and form a carbon-oxygen double bond, and R prime are still attached to this carbon here, which becomes this carbon. Well, same thing happens with a ring. Notice I don't lose R and R prime. Here's the carbon right here, this carbon, and it will be now double bonded to oxygen. And remember, we don't show it, but there was a hydrogen there. Now there isn't. And that's how you do rings. And now I'm really happy because Dr. White loves what's called cyclic ketones. All right, let's have you try some. And what would be the organic product or product for the following? I forgot to mention, I hope you all had a nice weekend. I got to do a lot of yard work because today is brush pickup where I live. And I had a pile that I moved Saturday afternoon. Yesterday it was too hot and I knew it would be, so I didn't want to work outside. But anyways, my pile in front on my parkway on the grass in front of my house by the curb is about make it 10 feet long and about 3 feet high. And it's about 6-7 feet wide. I did a lot of pruning and cleaning. Whoa, did I do? All right. Remember, thumbs up when you're done. All right, I think everybody's done. So let's take a look at this. We have what's different, oxygen with a hydrogen and a carbon. It's got carbons here and here. And this is a secondary alcohol. And if I oxidize it, that's what the O in the brackets mean. I lose this hydrogen, this one. And I form a carbon-oxygen double bond, which you'll learn later is called a ketone. Right now, you don't have to know it. Later, I'll teach you about it. And here, oh, look, R and R prime are the same. And they're still attached to a carbon, this one with the hydroxy group, OH. So I'll do that, keep them attached. And then this carbon, which is this carbon, becomes this carbon, which now is this carbon double bond to oxygen. And that's how you do it. Oh, let's do another one. I'm having fun. And why don't you have some fun too? What would be the organic product or products for the following reaction? 3 points each. All right, let's get going. We look at this molecule, what's different? Ooh, oxygen with a hydrogen on a carbon. I've got carbons here and carbons here. This is a secondary alcohol. And I'm oxidizing it in a ring. R and R prime are connected together, which you see here. Now, what happens? You lose a hydrogen there, and you form a carbon-carbon oxygen double bond. R prime and R double prime are still attached to that carbon. That was this carbon. So what that means is this carbon here is still going to be part of the ring. And the methyl group is going to come along for the ride too. And this carbon right here is this carbon, which means it will be bonded, double bonded to that oxygen. And Dr. White's smiling because that's a pretty molecule. And that's how you do oxidation. Oh, let's do one more. What would be the starting material that you would oxidize to make that molecule? You're doing organic chemistry. Hopefully it's not too painful. All right, I think everybody's done. Let's take a look. We're oxidizing something. That's what this means. And what are we making? What's different? Ooh, oxygen double bond to carbon. And let me rewrite it how you're used to it. There are different ways I could have written it, but let me stay consistent. And notice this carbon with the double bond to oxygen has carbons here and here, which I can call R and R prime. This so happens they're the same. And what do we start with? A secondary alcohol. And now the carbon that's double bonded to oxygen will be the carbon with a hydroxyl group on it, which is this carbon. So I can write it this way. R prime and R double prime are methyls. Or I could have written it this way. In either case, it's the same alcohol. 2-propanol, or otherwise known as isopropyl alcohol. And that's how you oxidize primary and secondary alcohols. Now, if we look, no, tertiary alcohols cannot be oxidized. Let's take a look why. And in the previous examples, we lose a hydrogen, and all right, hang in there. I gotta close Microsoft Word. And let me do my whiteboard. Yep, it knocked me out on its own, sort of. Let me do this. Sorry about this delay. All right, we're back. And excuse me while I sneeze. Excuse me. All right, now we have a tertiary alcohol, a secondary alcohol. You lose the hydrogen from here and here and form a carbon oxygen double bond. Well, there's no way between this and this oxygen I can form a double bond. Why? Because then I'd have 5 bonds to carbon, and that won't happen. So for oxidation of a tertiary alcohol, the answer is no reaction. Tertiary alcohols cannot be oxidized, and they can't. Now, one of the things I might have mentioned once or twice, but I'll mention again, I teach by my golden rule of teaching. And that is, I don't do to my students what I didn't like done to me when I was a student. When I took organic chemistry, I was upset when the teacher would put on a test this reaction, and the answer was no reaction. You asked me, give the product or products. You shouldn't ask me put down no reaction, because that's not a product or product. So what that means is on my test and final, the answer no reaction will never, ever, ever be correct. The answer no reaction will never, ever be correct. So what does that mean? I'll never put this reaction on. I'll never put a tertiary alcohol being oxidized where you have to write down no reaction. That's not right. So the only 2 oxidation reaction of alcohol is a primary alcohol and secondary alcohol. All right, let's move on. Now, good news. Mother Nature and organic chemists have different molecules where you can have more than one hydroxyl group in an alcohol. And I thought I'd teach you about a couple of them. One is an area called glycols. And I'm going to turn the switch off, but still, this is something important to know about. Now, the simplest glycol and the common name is ethylene glycol. And how they got that, well, I'm not going to go into it. I don't even know how they got the term glycol. The UPAC name, which I'll never ask, is 1,2-ethane diol, di-2-ol alcohols. And now this is ethylene glycol. Now this is a poison, but it's a very useful chemical. If you mix it with water, it forms a mixture, homogeneous solution, which we use. Where do we use that? It's used as your antifreeze. You have what's called the colligative effect, which you learned about in the melting point lab, but that can happen with liquids too. When you add ethylene glycol together with water, the boiling point will be higher and the melting point will be, disappeared, lower. So in the winter, when I got a whole minute to go, when it gets cold out, your radiator won't freeze when the temperature goes to -10 because you have ethylene glycol water. If you had water in there, your radiator would freeze, and probably because the expansion of the water bust. And years ago, that was a problem. In the summer, when it gets real hot out, your radiator won't start overheating because the water inside is boiling, because the ethylene glycol helps raise the temperature. Now, one bad thing, ethylene glycol is a very, very bad poison. And that's why if you look at your antifreeze, it's colored green. That tells you it's not water and you shouldn't drink it. So don't, please don't. Oh, guess what time it was? Time flies when you're having fun with alcohols. But anyways, it's time for our break. So I'll see you at 2:50. I'm going to take a 5-minute stretch break. Time to get going. Oh, let me use a different whistle. All right, give me a thumbs up if you're back. So I'm the only one with my webcam on. Thank you, everybody. All right, we're talking about alcohols, molecules with more than one alcohol in it. I was talking about ethylene glycol, which is used in antifreeze. Now, another molecule again switches off, but I thought I'd talk about it, and that's this molecule. And this is called glycerin. That's the common name, not the IUPAC. Again, switches off, and I'll never ask on a test. Sometimes it's called glycerol, but I haven't seen that in a while, but once in a while it is. But it's called glycerin. And glycerin is 3 carbons, and each one has a hydroxyl group. If the IUPAC would be propane, 1, 2, 3, propane, drop the E, then 3 hydroxyl groups triol. And this is glycerin. Now, I worked for a company, I'll talk about later when we get into fats and oils, and we made, I don't know, about 100 million pounds or more a year of glycerin, plus other things. Your body makes glycerin. Glycerin is one of the products that your body makes when you digest anything with a fat or oil in it, and you make glycerin. Now, because of all the hydroxyl groups here, one of the uses of glycerin is as a humectant. Now, humectant is a fancy word for something that keeps food from going dry. And there are other humectants. How many of you have ever bought those super soft, chewy chocolate chip cookies? There are a number of different brands, and tastes like it's just been made because it's still nice and soft, even though it's been in that package for a while. Well, they put in a humectant. One of them could be glycerin to do that. And glycerin is used in a lot of different other areas, which I'll talk about when we get into fats and oils. One humectant, which I might as well mention, remember I told you learn a lot about Dr. White personally. Back when I was a lot younger, I was addicted to smoking. What can I say? My father smoked, and I said I'd never smoke, and I got addicted. I was a heavy smoker. At one point, this is back when you could smoke cigarettes on a plane. I could tell you how many cigarettes I needed in my pocket of my shirt to go from O'Hare Airport to major airports throughout not only the United States, but world, because I did that kind of traveling. And I remember Detroit, and why do I still remember this? I don't know. 2 cigarette, New York, and really New Jersey was about 8-10 cigarettes. LAX, Los Angeles was about 12 cigarettes, depending how I was a chain smoker. And Amsterdam and Manchester, yes, I did go to those cities, was usually about a pack and a half. It was a long flight. And thank goodness, back in about, I'd say 1985, I finally realized smoking killed my father. Why am I doing this? It's going to kill me. And I gave it up. And luckily, I have never smoked again. And it helped me. So if you're smoking, give it up. Trust me, you'll like it. All right. And they use humectant like glycerin on the tobacco and a cigarette so it doesn't get dry, keeps moisture in there, so it smokes better. I know, I used to smoke. All right, let's talk about table sugar. Table sugar is an alcohol, but if you eat a lot of table sugar, which we call another common name is sucrose, you're not going to get inebriated, drunk. And let's just take a look at the structure. And again, switches off, but this is neat things to learn about. If you look up Wikipedia, which I think I might have mentioned, has been so heavily policed by organic chemists and chemists in general. And here's the structure of sucrose table sugar. Notice you have 1, 2, 3, 4, 5, 6, 7, 8. Actually, there are 2 more, 9, 10, but you don't see it in here. And I'll explain why in the cyclic structure. But there are a lot of hydroxyl groups, and this is sugar. And that also explains why sugar is so soluble in water, which is a good thing. So when you cook with sugar with something with water, it's good. It dissolves easily. Now, the last compound on this list is called polyvinyl alcohol, which is abbreviated PVA. And I think just about all of you or most of you have PVA in your house. No, I don't have polyvinyl alcohol. Poly means many, vinyl, I'll teach you, CH2, CH, double bond. But when you convert it, make it to this molecule, you lose the double bond, and it's called a polymer. And again, switches off, but it has this structure where N is a repeating unit like a lot of boxcars in a freight train. And N here can be on the order of about 1 million. Yes, 1 million. Well, this is called PVA, polyvinyl alcohol. Now, if you mix polyvinyl alcohol plus water, you get this white goopy stuff, and that you do have, and we call that Elmer's glue. And there are other companies that make that now too. And Elmer's glue originally was made by Borden. And I worked for Borden many years ago, Borden Chemical, that division. By about the time I started, they had sold the glue division off. And originally, before polyvinyl alcohol, they used a polyol, many, OL alcohol, that was called casein, that came from slaughterhouses, which in the old movies, if you don't be good, I'm going to send you to the slaughterhouse and they'll turn you into glue, which is one of the things, those byproducts that was used. But since then, they've gone to synthetic material, PVA. So next time you see white glue, like Elmer's glue, that's a polyalcohol, lots of them. And hydrogen bonds to things like paper and wood, and that's how glue works. Now, something I want to talk about, because it's something important for your daily life, but the switch is still off. And that's phenol or phenolic compounds. And phenolic compounds means a compound that contains a benzene ring with a hydroxyl group and other things on the ring. And these are amazing antioxidants. How many of you have heard antioxidants are good for you and can help keep you healthy? Give me a thumbs up. Any of you? How many of you seen the, was it pomegranate juice, where they talk about drink our product, it will help keep you healthy because it's got lots of antioxidants in it? I think that's the one with the dragon, one of their commercials. Why do I remember that? What's an antioxidant? Anti means it stops, and oxidation. Now, what I'm going to talk about is switches off. Now, air, the oxygen air can react with certain organic molecules, especially those of foods and lubricating oils. And this causes radicals. Now, I can do a whole, not one, but 2-semester graduate level course on radicals and their chemistry. In this class, we're not going to touch it. That's where you have a carbon with 1 electron, not a charge, not plus or minus, it's 1 electron. And we call this a radical. And radicals are very reactive intermediates that will attack, notice I use the term attack, react with many things to make new things. And you don't want this because if you have something like food, oxygen can react with some of the stuff in the food to make radicals, which make new molecules, which taste bad. How many of you have ever heard the term rancid? Like butter goes rancid, or how many of you have ever tasted crackers or cookies or potato chips that have been around too long, open, and they don't taste right? And we say, oh, that went rancid. That's because radicals were formed and they make new molecules that Mother Nature, a lot of them, made them taste bad to us. So we know, don't eat this, it's not good for you. Well, phenolic compounds react with radicals to form what we call more stable radicals that do not react with foods or lubricants. And 2 of the common ones that used to be used is BHA and BHT. Now, one of the common ones, BHT, has a common name besides the acronym BHT, known as butylated hydroxytoluene. That's not the IUPAC. And this is BHT. Now over here, oh, it's my favorite, a T-butyl group. Over here, T-butyl group, benzene ring, hydrox group. Remember, for a line, and I won't ever write alkyl groups in the line method, but every end of the line intersection is a carbon. So I have a methyl group here. And this and another one called BHA were used for many, many years in potato chips. Potato chips, because of all the oil in them, can go rancid pretty quick. Well, they used to put in the potato chips treat the surfaces with a dilute solution of BHT, BHA. And when I was in grad school, my mother would say, you're eating too many potato chips, you don't need it. I said, but Mom, it's got antioxidants that's healthy for you. She never bought into that. Now, a couple of years ago, maybe about 10, 12 years ago, organic chemists found a way to make the plastic bags that potato chips come in, also other foods, plastic containers like mayonnaise, in such a way that oxygen will not get through the side of the container bag. And because of that, you now buy potato chips and they don't put BHT and BHA in. But if you notice how it's sort of a puffy bag, they now put nitrogen in there to drive the oxygen out, seal it. The new bags keeps oxygen out, and that's why they have a longer shelf life. But once you open it, the oxygen gets in there. So you should eat it. But in my house, potato chips disappear, evaporate like that. They're never going to go rancid once the bag is open. Now, one of the interesting things about antioxidants, which why you see those commercials. How many of you have heard a while back that there was somebody who did research? Every time, once in a while, you hear about it. One is dark chocolate is good for you because it has antioxidants, or red wine is good for you because it has antioxidants. There's a theory, and I understand how antioxidants keep you healthier, that aging is caused by radicals reacting in our body. Is that true or not? I don't know, but antioxidants are help reduce that so you stay healthier longer. Is that true as aging? Don't know, but yes, I get my antioxidants in my daily food. All right. Uh-oh. Uh-oh. I better warn you about something. First of all, I'm going to turn the switch back on for a little while, but the next thing I'm going to talk about stinks. And I mean stinks. It is stinky. What stinks? Well, we're going to talk about thiols. Thiols are the sulfur analog of alcohols. What does that mean? Well, if this is an alcohol and switches on for this, where you replace the oxygen with sulfur, is a thiol. And these stink. Of all the organic chemicals, thiols are the stinkiest, all the chemicals, I think. And that's where you have hydroxyl group is replaced with SH, the thiol group. Now, I'm not going to ask you to learn the nomenclature, but they're like alcohols. Instead of using an OL ending, use a THI. Thi means sulfur, OL like an alcohol. And you use the same number in nomenclature, drop the THIOL. We're not going to cover that, but you should know they stink. Now, once in a while, when I learned organic chemistry, and for many years afterward, they used to be called mercaptans. About the late 1980s, or give or take 5 years, somewhere around then, IUPAC changed the name to thiol, and I still once in a while will call them mercaptans. So if that slips out, well, you'll know why. Now I'm going to skip this slide. What's the stinkiest thing you can think of? Well, how many of you ever been around an area where a skunk let loose, either on an animal or just let loose and miss, and you walk by and, oh, is that awful? Well, someone, and I'm glad it wasn't me, analyzed the weapon that a skunk uses, which is that spray. And they found this thiol with a double bond is 45%. This thiol with no double bond, a little different, is 25%. Probably the rest is water. And boy, do those stink. Now, what are other things that stink? Well, guess what? Onions and garlic stink, even though I love onions and garlic. They have a strong odor to it. Trust me, you don't want to be around someone who's eating a lot of raw onions or garlic. They stink. Now, this is an important story. Switches on. If I could turn a dial and only went up to 10, I just turned it to 40. T-butyl thiol, which is a common name for this molecule, stinks. And boy, this stinks. Oops, I wrote the alcohol. Sorry about that. I got alcohol in the brain. This thiol is T-butyl thiol. and it's added to natural gas to give it its odor. And now I have to tell you a very sad but true story. Back about 1935, there was this town in Texas. The high school was very close to an oil well field. And one of the things you generate when you pull oil out of the ground is methane, CH4. And the high school, instead of burning it, which a lot of oil well companies do, if you ever gone by an oil well field, you'll see sometimes in the old days a pipe with a big flame on top, and they're just burning off unwanted methane. Back then when it was super cheap and nobody wanted it, now they collect it and sell it as natural gas. Well, instead of burning it off, the company that owned that oil well field said to the high school next door and that town, we'll give you the methane for your high school free. Or it was a grade school, high school. I think it was a high school. And they said, sure. It was a newer building, or maybe, I'm not sure how new. And then a while later, it blew up. Over 135 students and teachers were killed like that. Hundreds more were badly burned and injured. Very sad. And because of that, well, first of all, what caused it? Back then, you only had natural gas methane, CH4, which is odorless. And there's two stories based on which the end results was the same. One was when they built that high school, they weren't that careful with the piping for the natural gas, and it leaked. And if you know about flammable gases, and I've worked with hydrogen, when you turn, see my light switch right there, when you turn it on and off, there's a little spark in there. If there's anything flammable around there, it goes off immediately. In fact, in the chemical industry, we have special things like phones, switches that are explosion proof. They're inside something. So even though you're moving a lever, no gas can ever get in there. Otherwise, you'd be dead. Well, one story is that somewhere in the machine shop where there was a lot of this gas, someone turned on a drill press, turned on the lights, and blew the place up. The other version was in the gymnasium, they were doing a chili social and to make some money for the high school. And who was ever cooking walked out of the kitchen, didn't realize the gas went out. You couldn't smell it because it was just methane. Filled the place up, somebody lit a cigarette or turned on a light and blew up, same thing. Well, anyways, because of that, the Texas state government at that time and the governor decided we need a commission to have come up with a way so that will never happen again. And this you should know. What they came up with, which was fantastic and has helped save lots and lots of lives, is they put a thiol mixed with natural gas. And that thiol is T-butyl thiol. I almost said mercaptan, which is the old name, but T-butyl thiol. And T-butyl thiol stinks to all high heaven. How bad? How many of you have smelled a gas leak or natural gas? Really, only one? Hey, well, a couple of you. You know how easy it is to smell it? Oh, gas. Well, how much T-butyl thiol did I put in methane so you can smell it that good? About 4 pounds of T-butyl thiol per billion, yes, billion pounds of methane. That's 4 ppb, 4 parts per billion. That's how stinky it is. Do I have time? Oh, I do. First of all, water break. Now, when I was in grad school, I went to Michigan State, and then when I started, it was a pretty new building, a beautiful building. It was like 2 blocks long, 5 stories high. It had a penthouse to do work in. It had a basement, a sub-basement, and a sub-sub-basement, all 2 blocks long. It was huge building, still is. And we'd have fire drills where you had to go outside and then the fire department would come, look around, they do their thing for a fire drill, and we'd go back in. Well, one November, fire alarm went off. When you're in a chemistry building with all the chemicals in there, you get out. And I grabbed my coat because luckily I was in my lab where I did my research, and so did the other grad students who were in my group. It was November, end of November, and we went outside. And usually after about 5-6 minutes, fire drill's over, you go back in. 5, 10, 15, 20 minutes, and we're still out there. It was sort of cold and misty, not fun weather to stand outside a building. And finally, someone asked one of the firemen, "What's wrong?" And he said, "We think you got a gas leak. We're looking for it." And back then, even I probably do it now, there are 4 branches of chemistry, 4 groups in a chemistry department: organic, analytical, physical, and inorganic. And the grad students, when you go out in a fire drill, the organic are all together, physical, the inorganic, and analytical. And someone in our group of organic and said, "I wonder what idiot dumped T-butyl thiol down the drain." And turned out about 20 minutes later, that's what they concluded. What happened was one of the workers for the chemistry department who worked in the sub-basement, gas leak. And what happened was, if you have traps that aren't filled with water that often, your sewer traps and whatever, if something gets in there, poured down the sink, it will go down there and come out that drain. Well, somebody, and it turned out it was an inorganic grad student, poured some T-butyl thiol to get rid of. How stupid could you be? Well, pretty stupid. That was it. Now, we had an award given to the chemistry grad student back when I was there. I don't know if they still do it, called the Barney Beaker Award. And the Barney Beaker Award was given to the grad student who did the dumbest thing that school year. And that student won hands down the Barney Beaker Award. It's not an award you ever want to get. I didn't, but he was, we let him know for a long time how stupid he was. Again, the important thing you should know is thiols stink, really. And a thiol is put in natural gas so you can smell it when there's a leak. Now, because the solubility and other reasons, physical properties are different, but it's very similar. Thiol is put into propane, the white tanks, so you can smell if that's leaking. And that's thiols. And like I said, next time you smell something where you have a skunk something, you're smelling a thiol. And guess what? We finished the alcohols and phenol and thiols chapter. And it's going to be new chapter time. Remember, this is for test 2. Now, I'll remind you on Wednesday, let's make it a week from today, a week from this Wednesday, I'll go through the alcohols problem set. So this weekend, part of next week, you'll have plenty of time to do it. Remember, keep up. That will help you. Actually, you'll find out Monday when you start taking test 1, why I call them practice problems. Hint, hint, wink, wink, say no more. If you don't know that, that comes from Monty Python Flying Circus. If you don't know about that, or you missed a good TV program, used to be on many, many decades ago, and still some of it on YouTube and other places. I'll look on some of the free internet stuff, like, and also not free, like Amazon Prime. All right, it's time for a new chapter. And what's that new chapter? Well, I better open it up first. Hang in there. That's not what I want. That's what I want. That's what I want. All right, let me make sure you can see it. All right, everybody see chapter 8, ethers and epoxides. Thank you. Now, this chapter, we're going to get into stuff. I'm going to tell you some personal story about a very serious operation I had, and that deals with ethers. And I'm going to be teaching you stuff that's really not even in the book if you're reading the book with epoxides, because I worked with this stuff at 2 different companies, and I know it quite well. And so what is an ether? Now, an ether is where you have an oxygen, and attached to that is R and R prime. Think of an alcohol where you replace the hydrogen on OH with an R prime, and we call this an ether. So that's an ether. Now, nobody uses the IUPAC nomenclature for ethers unless you have to, which means you need to do it for either a legal document like a contract or a patent. Other than that, even some patents use the common names. So I'm going to be teaching you only the common names. What do? Name each R group of the ether as an alcohol, switches on, by the way, now for test 2, and add the word ether at the end of the name. See board for examples. I better get to work. Now, let's take a look at this molecule. And the question be, what's the common name? And now we look at this, and just like I've been teaching you so far this semester, when you look at an organic molecule, look for what's different. Ooh, what's not a carbon-carbon single bond or carbon or hydrogen atom? Oxygen. Notice it's got carbons here and carbons there. It's different. So I use R and R prime, and this is an ether. Now, in common, you name this R group and this if we're an alkyl group. So the first one is methyl. The second one, that's an ethyl. And because it's an ether, I put ether at the end. Now, because this is a common name, there's no rules like IUPAC, so I could have easily written it ethyl methyl ether. And that's how you do ethers. So let me have you try one. Give the common name. For this molecule. 3 points each. Remember, name each R group on the oxygen as an alkyl group and add the word ether at the end. one of the things you may do is put your hand over the oxygen on one side and then look at that as an alkyl group and then do the other side. And when you're done, give me a thumbs up. All right, everybody's done, so I better get to work. If I look at this, what's different? What's not a carbon-carbon single bond? Carbon or hydrogen atom, oxygen. It's got carbons here, carbons here. They're different, so I use R and R prime, and this is an ether. And how do you use the common names? We look at this one, 2 carbons bond to something, that's an ethyl group. This side right here, 3 carbons, center carbon bond to something, in this case, oxygen, that's an isopropyl. And this is an ether. So I'm done. Oh, let's do one more. Two more rings, my answering will pick it up. One more ring, let's say hang up. That's all. Sorry about that. And that is the compound give the common name for. Your turn. While you're doing that, I'm going to sneak off and look up something I need to look up. All right, let's do this. I think everybody's done. What's different? Ooh, an oxygen. And it's got carbons here and a lot of carbons here. And I think I'm going to sneeze in a second. So I think I stifled. No, I didn't. Excuse me. That was a slow evolving sneeze. And this group right here, if that was attached something, we call that a methyl group. This thing, 6 months ago, you would know CH3 was methyl group. Think about all you've learned in my class this semester. And 4 carbons to the N carbon is called N-butyl. So we could call this methyl N-butyl and R prime. This is an ether. So at the end, ether. And that would be methyl N-butyl ether. You could have put down N-butyl methyl ether. And that's how you do common names of ethers. Now, switches off for this slide. But in case you're wondering, yes, there's IUPAC nomenclature rules for anything chemical, especially organic. Now here, again, switch is totally off. Name the smaller alkyl group of the ether as an alkoxy group. Alkoxy means OR, bonded to something. Name the larger group as an alkane, like we did, find the longest chain. Then name and number the alkoxy group as a substituent on the larger alkyl group. Again, switch is totally off. Let's go back to the example we just did the common name. We look at C, the longest chain here is 4 carbons. That's butane. The alkoxy group is this, and that's called methoxy. Yes, I know these rules from. And this is carbon 1. So this would be 1-methoxybutane. Which is easier, methyl N-butyl ether or 1-methoxybutane? Well, organic chemists are lazy, and this is why we use common names, because it's easier. So I will never ask you what's the IUPAC name of an ether, but I can ask you what's the common name. Or let's do this one. I'm going to let you try one. Let's see if you can draw that molecule, methyl N-propyl ether. Thank you, Megan. And it looks like everybody else is done too. How do you decode it? You start here and move from the right to left. Ether, I know, is this. And this tells me what R and R prime are. 1 is the methyl group, and N-propyl, 3 carbons. Now, you could have also written it this way, and both are correct. Because molecules are not glued on a piece of paper, they rotate, and which is correct, A or B? And the answer is they both are. Those are identical. Left hand, still left hand. Now I'm going to turn the switch off, click. This won't be on the test, but it's important to know. Ethers, the smaller ones, which are mainly used in organic chemistry, not always, but mostly, are low boiling liquids, and they're flammable. Let's look at the following ether. Now, this is the most widely used of all ethers. The one common name is diethyl. Those 1, 2 ethyl groups, so we use ether. But it's so commonly used, sometimes it's just called ether. by many people. And this stuff is flammable. How flammable? Well, one of the interesting things about ethers are they're denser than air, all around us. So that means if you have any ether vapors, they stay right near the ground. Now, when I was an undergrad in organic chemistry lab in a 2-semester, and also other labs too, organic, you took a lot when you were undergrad where I went. We had my first year organic, our lab was known as the fire lab, because out of 16 weeks, we had 15 fires. Luckily, nobody was severely hurt or anything, but it was an exciting time, not. But anyways, we would use ethers, and we also use Bunsen burners, which nowadays you don't allow in an organic lab, any flames. And people would pour their ether down this trough in the middle of the benches that go into the sink at the end before environmentally sound laboratory practices. Everything went down the drain. But this is a long time ago, back in the 69. Wow, that's a long time ago. But anyways, and people would light a Bunsen burner with a match, and instead of blowing it out, would throw it in the trough. Now, if there was ether there, whoosh, you'd have a fire, because if you have vapor here and spread all the way like this, guess what? A match over here, and you got a wall of flame going that way. Exciting times. We had our graduate student who was the graduate assistant or TA for the lab, was this little Chinese guy, really little. He must have been about 5'3", if that tall, and very skinny. Dr. White's not short or skinny, but anyways, and back then we had the old fire extinguishers that were about 3 feet high and were heavy. This guy couldn't pick it up, but he could get it off the wall and drag it real quick. And that's ethers. Now, one of the uses, and I'll talk more about it on Wednesday, I think I'll have time, is diethyl ether is the first inhalation anesthetic. And what is an inhalation anesthetic? When you go for an operation, you want to put the person out, and you make them breathe in something, and it knocks them out. And the first one was diethyl ether. That was found about 1840, but turned out that was not safe because diethyl ether is extremely flammable. If I look at the clock, I'm just about out of time, so I think I'm going to let you out a whole 45 seconds early. Don't tell anybody, I'm being nice. And with that, don't forget, tonight I have my office hour from 5 to 6:15 on Zoom. If you need any help, stop by. Don't forget, this Wednesday, the lab we did last week is due, so get it in. And with that, also remember, on Wednesday after our lab, I'll send out the password for test 1. You'll have until Thursday morning to take test number 1. With that, I'll say, gang gesund, be healthy. Don't forget to wear your mask. Get a vaccination if you haven't already. And bye, gang gesund. I'll see you on Wednesday, unless you come to my office hour. And if anybody has any questions, I will stick around. You're welcome, Calvin.